evening, everyone. What's going on? All right, okay. Welcome to the environmental lecture presented by the American Chemical Society Pittsburgh local section. My name is Ron Hong Lin, and I'm a member of the ACS Pittsburgh local section executive board and chair of the environmental group. The ACS Pittsburgh local section is dedicated to building a vibrant and a sustainable community through the power of chemistry. The environmental group is one topical group within the local section formed with the aim of educating and promoting awareness about our environment. We support a variety of activities, and tonight's lecture is the fourth of this year. And we intend to continue the lecture series with a variety of speakers from academia, industry, as well as other research institutes, and cover various chemistry and environmental science related topics. And just let me let you know that the lecture is being recorded and will be posted on YouTube later on. And I'd like to remind the attendees and future viewers that the views and opinions expressed in this and any future lectures are solely those of the presenters and do not necessarily represent the views of the ACS Pittsburgh local section. Now, it's my great pleasure to introduce tonight's speaker, Dr. Wen-Chai Zhang. Dr. Zhang is currently an assistant professor in the Department of Mining and Minerals Engineering at Virginia Tech. He received his PhD degree in mining engineering from the University of Kentucky. His research focuses on the sustainable recovery of critical elements, such as rare earth elements, from various resources, with support from many funding agencies and industrial stakeholders. His research group has developed several innovative concepts, flow sheets, and techniques for the recovery and purification of critical elements from complex, solid, and aqueous streams. Dr. Zhang has authored and co-authored more than 60 peer-reviewed journal articles and many conference papers, and holds several US and Chinese patents. He also served as associate director, editor, and editorial board member of several prestigious journals in his field. With that, please join me and welcome Dr. Zhang. And also thank you everyone for joining tonight. Thank you.
Thank you. Thanks for the introduction, Dr. Lin. I'm going to share my screen and we start my lecture. Yeah, thank you very much. Yeah. Okay, can you see my slides?
Yes, thank you.
Okay, great. Yeah, great. The title of the lecture is Rare Earth Recovery from Coal-Based Materials and the Progress from Feasibility Assessment to Pilot Scale RE Production. So I think it's still related to environmental because the feedstock we used is waste generated from the coal mining activities. So it's very related to the environmental aspect. And I really appreciate the invitation from Dr. Hong Lin actually for this to give this lecture, to share the findings actually we achieved over the last few years. And so our opinion on this topic. As you can see, actually, this is let me put out the laser. This is a picture, SEM EDX picture of a rare earth particle we found from coal refuse. As you can see, actually, this is a very good rare earth phosphate mineral. From the figure, you can see that. And actually, we can define this as a monazite particle in the coal refuse. Monazite is very common rare earth mineral, and normally it occurs as a separate ore deposits, but sometimes you can also find this kind of mineral in coal deposits. So this is what I'm going to talk today. So first of all, I'm going to introduce critical elements, and then I'm going to introduce the rare earth elements in coal, and the rare earth elements recovery from coal refuse, and rare earth recovery from acid coal mine drainage. and rare earth elements recovery from coal fly ash. And in the last section, I'm going to introduce something about the pilot scale rare earth elements reproduction. From here, actually, we use coal as a tool for power generation, but coal refuse, acid coal mine drainage, and coal fly ash, all these are the waste generated from the coal mining and the coal combustion process. So we focus actually on the rare earth recovery from coal byproducts. So in terms of critical elements, actually, the first time actually people know about critical elements is in 2011. So this is something done by the DOE. Actually, they initiated a survey based on two factors. The first one is the supply risk. The second one is the independence to the clean energy. So basically, they evaluate the supply risk and the independence to clean energy, importance to clean energy based on these two factors for every metals. And they found that actually for certain metals such as dysprosium, it has a very high supply risk, but it is very important to the clean energy. At that time, actually, so they define these 5 rare earth elements as critical elements. That's something actually was done in 2011. After a few years, in 2018, DOI actually, they re-evaluated this kind of list of the critical metals, and this time actually a lot of metals were included in the new list. For example, in addition to the for the rare earth elements, all the rare earth elements are included as critical elements, and also some other metals such as lithium, nickel, cobalt, manganese. These are also included as critical elements. But the criteria for this kind of evaluation is the same. So basically, it's based on the supply risk and importance to the importance to clean energy. So this is a most recent actually a critical mineral list released by 2022. There are 50 minerals on this list. So all these minerals are very important to the clean energy, but it has a very high supply risk to the United States. So the reason actually why these elements becomes critical is because we want to develop clean energy. For example, this is a prediction of the growth of electric vehicle market as a function of time. By 2030, as you can see, the number of electric vehicles will be 10 or 20 orders of higher than the 2020 or 2021. So which means that we are going to manufacture a lot of electric vehicles. But as you know that actually to manufacture electric vehicles, we need a lot of battery. So the most common battery is for electric vehicle is lithium iron phosphate battery and NMC battery. So to manufacture this kind of battery, we need a lot of materials. For example, we need lithium, we need manganese, we need cobalt, and also we know that the motor. If we want to manufacture a motor for electric vehicles, we need to have a permanent magnet, and the raw material for the manufacturing of a permanent magnet is rare earth elements. So that's the reason why actually this metal becomes critical, because we want to develop clean energy. So this means that we are going to manufacture a lot of electric vehicle, and to manufacture a lot of electric vehicle, you need to have a very good supply of the raw materials. And the same for the wind energy. So this is the expansion of the growth of wind energy. For example, in 2019, and this is the wind energy is this size, but in 2023, 2035, this is a wind turbine size. As you can see, we want to increase the capacity from 2.5 million watts to 5.5 million watts. If you want to increase the size of the wind turbine, you need to manufacture actually a lot of the turbines for this kind of for wind turbine. So as you can see, this is a raw material as we used to manufacture wind turbine. So for each wind turbine, this kind of wind turbine has a size of 3 million watts. You need to consume 2 tons of rare earth elements. You also need to consume a lot of zinc, a lot of aluminum, and the concrete, steel, and copper. But based on the supply risk, rare earth actually has a very supply risk. But if you want to develop wind energy, you need to manufacture a lot of more wind turbines. And in this case, actually, since rare earth elements have a very high supply risk, So the rare earth becomes very critical for the development of wind energy. So the logic statistics is very easy to understand. So the US actually, it has some production of rare earth elements. For example, based on the data from USGS in 2022, in 2020, around 15.8% of rare earth is produced in the United States. But if you check the rare earth reserve in the United States, there is only around 1.3% of the rare earth distributed in the United States. So this amount of the rare earth is very small, a very small proportion. So which means that it means there is some production of rare earth in the United States. There is still a very high supply risk of this kind of critical metals. So now let's talk about the rare earth in coal. So coal, actually, we know that we saw it's black and it's dirty, but it takes hundreds of million years for coal to be formed. As you can see, it passes through several different stages. At the beginning, it existed as a pit. And after many, many years, it goes into the form of lignite. And then under the function of pressure and heat, lignite is converted to coal. So in this process, due to a couple of functioning mechanisms, rare earth goes into the coal deposits and makes the coal actually as contains much more rare earth compared with the earth crust. So the enrichment, geologists actually summarized the enrichment mechanism as four different categories. For example, the heterogeneous enrichment, tapestrious enrichment, infiltrational enrichment, and hydrothermal enrichment. So due to these mechanisms, actually the average rare content in coal is around 70 milligram per kilogram. So this is on whole sample basis. So because coal contains a lot of organic matter, so if you combust the coal and then get the ash residue, the rare earth content can go up to around 500 milligram per kilogram. So the content is higher than the earth crust, but it is still much lower than the rare earth content of the conventional ores. But we want to say that because there is a lot of coal in the United States, I want to show you this figure. For example, as you can see, this is a coal reserve worldwide distribution. In the United States, 22% of the coal in the world is distributed in the United States. So with this large reserves of coal, actually, even the rare earth content in coal and coal deposits is lower, but the overall reserve is still very encouraging. And in particularly, actually, in some coal deposits, it has a very high rare earth content compared with the average content. As you can see this in these slides, this is some sample we collected from the fire clay coal sample. The fire clay coal seam actually is located in eastern Kentucky. As you can see, this is rare earth content in different segments of the coal seam. There are some segments with a rare earth content actually of hundreds of ppm. For example, there is a flint clay coal segment of the fire clay coal sample. The rare earth content actually on whole sample basis, it can go up to 500 ppm. This is much higher than the 70 ppm that I was talking about. So, so we know that there is rare earth in coal, and in some coal deposits there are much higher rare earth content compared with the average content. But we want to know what's the mineral form of rare earth in coal. In general, actually, the occurrence mode of rare earth in coal can be classified into three categories. First one is minerals. So basically, some rare earths actually existed as minerals in coal, and the second one is unsubstitution in clays, and the third one is organically associated. So based on my experience, research experience, I think the first one, the minerals, and the third one, organically associated, are the major contributors for the rare earth in coal. We did a lot of tests. We didn't find the coals with clays with unsubstituted rare earth in coal seam. So which means we don't think this is a very dominant contributor to the rare earth in coal. So as you know that when we mine coal from the underground, after mining you get we call it a run-of-mine coal. This kind of coal actually cannot be directly combusted because there's a lot of rocks actually being mined together with the coal. So which means we need to do some processing. So we call it as coal preparation. And then we separate the run-of-mine coal into different products. So basically we get a clean coal. As you can see, this is a black, sunny black color. This is material we call it clean coal. And then this can be used for power generation. And then as we get some coal waste, and we can also, sometimes we call this as coal refuse. So basically this is a high S content, the rock portion of the run-of-mine coal. And this is normally rejected actually. So it will not be, it is not beneficially used. And also, as you know, that there is a lot of pyrite in coal deposits. So once you mine, you mine the coal out from the underground, so the pyrite is exposed to the air, oxygen, and the moisture. So under these functions, and the pyrite is dissolved. Because the pyrite is dissolved, actually it generated some sulfuric acid. So the sulfuric acid will reduce the pH of the water. So this kind of water, we call it as acid manganese. So as you can see, this is a coal refuse pond. So it contains a lot of coal-fired refuse. So we collected some samples from coal refuse pond for research of our work. And this is shows you a coal power plant. As you can see, clean coal goes into a power plant and it combusted, generate energy, and the energy is used to drive a turbine to generate electricity. But in the same time, actually, because there are still some S content in the clean coal, so after combustion, you will generate some residue. We call this as coal combustion S, which can be coal fly ash and coal bottom ash. So I'll talk about the generation mechanism of acid manganese. So basically, acid manganese is due to the formation of sulfuric acid due to the oxidation of pyrite and the function of oxygen and moisture. So now let's talk about the rust recovery from coal. As I mentioned, actually, after coal preparation, actually, it generates different products. So for example, you have coal refuse, you have clean coal, you have coal-fired refuse. And there was a survey based on about around 20 coal preparation plants in eastern US. And what they did is that they collected the samples from each stream in the coal preparation plants. And they found that in average, around 22.5% of errors in the run-of-mine coal goes to the coal refuse. And only 15.7% of errors in the feed goes to the clean coal. And 11.8% of errors in the feed go to the fine refuse. So this is interesting, okay? It tells you that if you want to recover errors from coal, and you need to go to the coal refuse because there is over 70% of errors in the feed goes to the coal refuse. So this is the reason why at the beginning we focus on errors recovery from the coal refuse. So we did a lot of physical separation tests. For example, we want to separate the rare minerals based on the density difference, surface chemistry difference, and magnetic property difference. But we didn't get a lot of success. So I think the major reason is the rare mineral particle is so fine in coal refuse. Mostly it's less than 5 microns. And sometimes those particles are encapsulated with major minerals. So in this case, actually, it's very difficult actually to use physical separations to separate the rare mineral particles from the other particles. So lately, actually, we do some chemical recovery work. We call it leaching. So basically, it's very easy to understand. So you mix the solid particle with a solution that contains some chemicals such as sulfuric acid. Because the acidity of the solution is low, so some minerals will be dissolved. So in this way, you can get some recovery of the rares from the coal refuse. We did a lot of work, and we find that for most coal refuse, actually, the rare minerals are very difficult to be dissolved from the coal refuse with mineral acids such as sulfuric acid. This table shows you actually some data, some results that we obtained. Actually, it tells you that the recovery from the coal refuse are very difficult to be achieved using leaching alone. So then we can go back for the major actually the commercial resources of rares are ore deposits. For example, you have bastnasite, you have monazite, you have xenotime. And when people process these kind of minerals, they normally use a technology we call it roasting. So it's easy to understand actually. So basically, you mix the minerals with some additives such as calcium oxide, sodium chloride, and calcium chloride. and you mix them together and you roast this kind of mixture at high temperature. In this case, the rare mineral will be converted to another chemical form, and this form will be much easier to leach compared with the original minerals. So this is a roasting. So roasting is very normally used in the rare earth industry actually to increase the leachability of the rare earth minerals. But because actually at that time we found that rare earths in the core refuse are very difficult to be leached, then we think so we try roasting actually to improve the leachability of rare earths from the core refuse. But there is an issue actually. There was an issue that we know because if you want to add additives, actually this means you need to cost some money to buy this kind of additives. So this will increase your recover cost. So what we did is that we just roast the sample at high temperature without adding any additives. Okay, this is some work actually we done in the March of 2018. So we think actually it may work or it may not work, but finally we found that it works well. So this is the results actually we obtained in 2018. For example, this is a total rare earth lithium recovery, and the original lithium data is here. So this line is the lithium recovery of rare earths from the raw core refuse, and the line above actually this is core refuse, the lithium recovery of rare earths from core refuse. Roasted at high temperatures. For example, the highest we got is roasted at 600 celsius degrees C. So this is interesting actually. So we didn't add any chemicals during the roasting, but we found that the rare earth lithium recovery is increased a lot. I mean, we increased from around 10% to over to 80%. So this is encouraging, but also confused us because we don't know why, because we didn't add any additives into the system. So we proposed some mechanisms. The first one is dehydration. We think that the dehydration of the clay minerals actually this may contribute to the enhanced lithium recovery of rare earths, and also the dehydration of clay minerals can contribute to the liberation of the rare earth minerals. And also we propose the thermal decomposition. We think there are some rare earth minerals is not we observed as the conventional, such as monazite, zeolite, or bastnasite, but this may be some rare earth minerals that we barely see and but exist in coal and high temperature. This kind of mineral can be decomposed. And we also think that physical assemblies, can be a very big impact factor actually can choose the lithium recovery. So all these three mechanisms that we approved are true in our research in 2022. So we did a lot of SEM analysis and some other characteristics. We found some new rare earth minerals from the core refuse, and we also found that the physical assemblies and dehydration are very important. So I'm saying these are the correct mechanisms to explain the enhanced lithium recovery. So now, next, I'm going to talk about rare earth lithium recovery from acid coal mine drainage. So here is a description of how the acid mine drainage is generated. So I'm not going to repeat it again. But you know that because the acid mine drainage has a high acidity, the pH value is normally around 3, and sometimes you can see an acid mine drainage with a pH value of less than 1. So in this case, actually, because of acidity, some minerals will be dissolved from core refuse, and those minerals may contain actually rare earth elements. As a result, actually, you can see some rare earths in acid mine drainage. And if you, the highest concentration and soil is around between 6 and 7 ppm. So which is higher to me. And what we did is that we developed a process that can pre-concentrate actually the rare earths from the acid mine drainage. We call this as staged chemical precipitation. So the concept is very simple. So different metal ions in acid mine drainage have a different precipitation pH range. If you can choose the pH range and collect the precipitate formed in the range where the rare earths are precipitated, then you can get a pre-concentrate of the rare earth elements. So what we did is that we increased the pH of acid mine drainage to between 4 and 5. And in this case, in this pH range, as you can precipitate and remove iron and aluminum. And after that, you can do filtration. And for the filtrate, what you can do is that you can further increase the pH value to around 7. And then you can precipitate and obtain rare preconcentrates. And if you further increase the pH value to 9 and 10, you can precipitate and obtain the preconcentrates of cobalt, nickel, manganese, and zinc. Okay, the concept is simple, but we got a patent awarded actually in terms of this technology. So based on this method, so as you can see here, so this is a stage precipitation process. So what we collect the preconcentrates of the rare earths and we redissolve the precipitates. We get a solution with a high rare earth content, and then we did some oxalic acid precipitation test. And with one stage of oxalic precipitation, you can generate a rare earth concentrate of with around 98% of purity. So which is very encouraging. As I mentioned, the feedstock of the acid only contains around 6 ppm of rare earth elements. But after this simple process, you can get a concentrate precipitate actually that contains 98% of rare earth. So this is a huge enrichment of rare earth through this process. And finally, actually, we test this process in parallel scale, and it works pretty good. So, and we also modify this process, and not only high-grade rare earth product, we can also produce high-purity nickel and cobalt product. Yeah. So the next one is the rare earth recovery from coal flies. I know that Dr. Zhong Hongli has worked a lot on this topic, so he knows better than me. I just want to share, and also I didn't do a lot of work on this topic, but I read a lot of papers, and I want to share my understanding about rare earth elements recovery from coal flies. So in many studies, it has been found that actually rare earth in coal flies has a low leachability. And a lot of researchers actually did sequential chemical extraction. And they found that actually the reason why the rare earths are very difficult to leach from coal flies is because the majority of rare earths are in the silicates and aluminum silicates of the flies. As you know that actually during the coal combustion process, the silicates and aluminum silicates actually they become glassy. They don't have a very good crystal structure, and this is just a amorphous glassy structure. So which means if the rare earths are in the glassy structure, if you want to recover the rare earths, you need to break the glassy structure. And as you know that the glassy structure is very stable, and you need to very harsh leaching conditions to destroy the glassy structure. So this is the reason why actually RE recovery from coal flies is kind of difficult. This is because, I mean, rare earths actually they are in the glassy structure. However, actually, as you know that, as I mentioned at the beginning of this presentation, that compared with coal, because the organic matter in coal has been already removed from the coal, so the rare earth concentration in the coal ash and coal fly ash is much higher than the coal. So it is still worthwhile actually to evaluate to develop some technology for rare earth recovery from coal fly ash. So the content of rare earth in coal fly ash is around 500 ppm level, which is much higher than the coal, which is only 70 ppm level. So this is a figure actually in a review article that I'm published with the other people. So this is my understanding about how you want to recover rare earths from coal flies. So first of all, you can do a little bit of physical separations because it has been proved that rare earths can be concentrated to a certain degree by physical beneficiation. In most cases, actually, rare earths are more enriched in the non-magnetic fraction and also fine size fraction. So which means that if you use magnetic separation and sieving, you can get a fraction from the coal flies with a high rare earth content. This is meaningful actually. If you do, for example, if you do the physical beneficiation, you increase the rare earth content from 500 ppm to 1000 ppm, which means that if you use the same downstream separation and purification procedure, your overall cost, I mean, to produce a certain amount of rare earths will be reduced by half. So that's the reason why it's so important. And after you get that fraction, you have different options. The first one, you can do the roasting. So roasting pretreatment is you can roast that fraction with sodium hydroxide, sodium carbonate, calcium oxide, and some other chemicals that can react with the glassy structure. And after roasting, actually, you can do some leaching test. In this case, actually, after roasting, the glassy structure is already broken, so it can be easily leached and into a solution by reacting with acid, water, or salt leaching, and some other excipients. Okay, and another process is what you can do is that you can use alkaline leaching. So you know that as aluminum silicate, actually, they can be unstable and alkaline conditions. So in this case, actually, if you dissolve, for example, dissolve aluminum from the glassy structure, so the structure is broken, and then you can do acid, water, or salt leaching to dissolve the rare elements. Okay, and a third approach is you can directly go to acid, water, and salt leaching. But as I mentioned, this approach is difficult because rares in the cold flies is very difficult to release. And once the rares are dissolved into a solution, what you can do is that you can do rares purification. So there are many different ways you can do for rares purification. For example, solvent injection, selective precipitation, selective absorption, membrane separation, and some other separation technologies can also be used. So in this process, actually, you can achieve the recovery of rares from cold flies. But as I mentioned, actually in cold flies, there is only around 500 ppm, which is 500 milligram per kilogram of rares in cold flies. So even you achieve 100% recovery of rares from the cold flies, you only use a very small portion of this material. The majority of the material is still waste. So which means you need to find a way actually that can reuse that can use the remaining material. In this way, actually, you can achieve the complete valorization of the cold flies. So which means that actually when you recover rares, you need to consider some other uses of the remaining material, such as aluminum recovery, zeolite preparation, supplementary cementitious material preparation, and others. Okay. So pilot scale of rare elements production. So so this is a project led by the University of Kentucky, and I'm involved in this project because at the beginning, actually, we have been working on this topic together for around 10 years. So we first started in 2014, and this pilot plant was established in 2018. As you can see, actually, a lot of technologies and I introduced, I employed in this plant. For example, you have roasting. In this circuit, you have roasting, and this is a roaster we used in the pilot plant. And also you have precipitation, stage precipitation, as you can see here. As these tanks actually are used for the stage precipitation. And after stage precipitation, you can directly go to oxalic acid precipitation. What you can do is you can do solvent injection. So this is a solvent injection line. Okay. And after that, actually, you can do oxalic acid precipitation to get your product. So we also have a very small line for the oxalic precipitating rares, but which is not shown in this picture. The line is very small, and this is also understandable because the rares content in cool refuge is so low. So there's only around 300 milligram per kilogram of rares in our feedstock. So at the end, I want to introduce that for coal and coal refuels are secondary resources, and primarily in secondary resources rare earths, but there are also all other resources can be exploited and has been exploited for the rare earth recovery. For example, you have the sargassum, seaweed, algae, bauxite residue, phosphate production byproduct, and you also have geothermal bronze. These are I mean, there are some ongoing research actually for rare earth recovery from this kind of secondary resources. So the purpose is the same actually. We want to make sure the U.S. has a very secure supply of rare earth elements, and to support the development of clean energy. In summary, actually, rare earth recovery from coal-based materials has progressed from feasibility assessment to pilot scale production. And I know that some team is trying to build a commercial plant, But I would say that actually the economic viability of rare earths recovery from coal-based materials still need to be improved. The major factor is that the rare earths content in coal-based materials are still too low compared with some conventional rare earth ores. For example, I'm working on a project with MP Materials, and we operate the only rare earth mine in the United States, which is the Mountain Pass rare earth mine. And the toolings, which is an invaluable product that they generated during the mining and the processing process, contains actually 1% of rare earth. So which is unbelievable. 1% equals to 10,000 ppm, which is several orders of magnitude higher than the rare earth content in coal-based materials. So this is the reason actually you can see why the economic viability of rare earth recovery from coal-based materials still needs to be improved. Okay. And technically, we will see that there's no problem to generate reverse.
Hey, Wentai, I think there's a connection issue. Can you hear me?
Yes, Ronghong, I can hear you. It's Ed. So you're coming through fine. I'm not sure what happened to our speaker.
Yeah. We lost him. Okay.
Hi, Dolly. It seems I was lost.
Hey.
Yeah. So where was I cut out? Yeah. Can you hear me?
Yes.
Okay.
Yes, we can hear you.
So let me see. So did I cut out at this slide?
Yes.
Okay. So this is the end. So that's good. Yeah. So that's the end. Thank you very much, and I'm very glad to discuss with you about this topic. Yeah.
All right. Thank you, Dr. Ang. Thank you very much. A very interesting talk.
Yeah, that's right. Yeah.
So I have a question. So about the AMD, and you show very exciting like achievement that can enrich the rare earth element from ppm level to about 98%. That was just amazing. So I have question is what the recovery? Like you have very high concentration purity, but the recovery, what's the recovery when you do the precipitation at pH level around 7?
Yeah, the recovery is also high. I think our overall recovery is higher than 80%. This is because actually the precipitation pH window of yours is very narrow. So basically, you don't have to increase the pH value from 3 to 10 to collect all the rare earths. Actually, the majority of rare earths precipitated in a very small pH range window of 5 and 7. So between 5 and 7, you can get almost 100% of rare earths precipitated.
Oh, that's very.
Thank you.
Okay. Yeah. All right. So yeah, we open to the audience. Do we have any question from the audience?
Ronghong, I'd like to ask a question.
Oh, go ahead, Ed.
So what would be a economically viable concentration of a rare earth element in acid mine drainage water? So, here in Western Pennsylvania, where I am, we have a lot of AMD water. But if
Yeah.
I went looking for
Yeah.
what would be a reasonable or expected amount of, you know, an rare earth element in there?
So the S manganese is kind of special because the rarest concentration in S manganese depends on weather, and also the rarest content is in the host stuff, host material. In most cases, actually, in the S manganese, the rarest content is less than 1 ppm, and also we need to keep this concept this in mind. It's less than 1 ppm, but there is an advantage of S manganese because you know that the mining companies, they need to precipitate and neutralize S manganese in any way. So they need to add some alkaline to increase the piece value of S manganese, and then actually you can discharge it. Otherwise, you will be punished if you directly discharge it, which means that actually the chemical consumed, what you can do is you can incorporate this kind of state precipitation process into the existing S manganese processing process. So you just control the piece, and you collect the precipitate form in 30 pH range. And the mining companies, they will pay the alkaline cost for the precipitation. So in a word, I think actually if you have S manganese errors of a few ppm, for example 5 ppm or 10 ppm, it can make the process economical. That's based on the mining companies, they are willing to pay the cost of the alkaline of the base. Yeah.
Got it. No, it's very interesting because it's actually owned by a water authority that I work with, and there's
Okay.
12 ppm manganese in their AMD water. So they have a passive remediation site, and it starts with 12 ppm. By the time it gets to the reservoir, they've cleaned it up.
Yeah. And actually, I want to mention that the manganese is cheaper. Yeah. So if you have 12 ppm manganese, actually, maybe it's not very economical to exploit. Manganese actually is cheaper, much cheaper than the rare elements. Yeah.
Got it. Yeah, I haven't looked for the rare earth elements. I was just curious. Thank you.
Yep, you're welcome.
Any other questions? Okay, Wentai, so DOE has been investing in this area for more than 10 years, I guess, right?
Yeah.
So where's the technology stand right now in terms of RE from coal or coal refuse?
Zonghong, actually, as you know that I know that there are two teams selected to for proposal actually by FOA. That FOA focus on the build of the first commercial rare earth recovery plant from coal-based materials. And yeah, the first feedstock in the one project is S manganese. The other one is in lignite. So as you know that lignite, as reverse in lignite, is easier to leach and the content is also higher. But that's a progress, and the DOE is still put a lot of money in this area, but they focus on the building of the commercial plant. Two teams have got selected, and we will see. I mean, we will see whether they can. I mean, the money, whether the economic aspect can support the running of the commercial plant or not. Yeah.
Oh, I see. Okay. Yeah, very exciting. Still, this field is still, I think, DOE is continue investing in this area.
Yeah. And I want to mention that I see a lot of funding agencies actually they turned the focus from coal and coal-based material to other resources. Basically, right now they are exploring the recovery of rare earths and some other critical elements from different kinds of secondary feedstocks. Yeah. As I mentioned, algae, seaweed, and different something that you think very interesting. Yeah.
Yeah, and also I think there's expanding the category of the critical from rare earth element to critical elements and including other elements as well. So to basically want to try to make this technology economically viable.
Yeah, that's right. Yeah, that's right.
All right.
I think there's still a lot of work can do actually because it's very related to environmental. We know that all the feedstocks, if you don't recover your earth, I mean, they will be disposed and this will cause some environmental concerns. So it's all these are environmental, yeah.
Yeah, you're right. And especially there's some accident related to like fly ash and other waste. So yeah, you're right.
Yeah, that's right, yeah.
Do we have any other questions from the audience? If not, let's thank our speaker again. Thank you, Dr. Zhang, and thank you very much.
Thank you, Dr. Lin. Thank you very much. Yeah. Have a good evening.
And thank you everyone for attending tonight's lecture.
Okay, thank you. Bye.
And have a good evening. Bye-bye.
Yeah, bye. Bye.